Hello, everybody. Welcome back. Yay. We're here again. Yeah, it's been ages. It's been ages and ages since we last done one of these. We've been doing them online, but it's not as good as being here in person and in a nice new venue. So thank you, Inpay, our hosts. So Copenhagen Ruby Brigade, you probably know that's why you're here. Just in case you didn't know, you're here. And this is what we have on the agenda for tonight. So you know what's going on for the first half an hour. You just had that. Cats, drinks, great fun. We're going to have an introduction for organizers. Us, so hello. And then we will have a message from our nice new hosts in the debate. So Mikkel, do you have something that you want to say in 5 minutes-ish?
A little bit more than 5 minutes.
5 minutes? I think we had 10 minutes.
Sure.
Perfect. And then we'll have our first speaker, Stephen Best. He's spent too much time doing something ridiculous in Ruby. So I think Best described as an excellent waste of time. And then we'll have a food break, again sponsored by Inpay, so thank you again. And we have our second speaker, Ignacio. He's going to be talking about some Kubernetes things, some Ruby. And then we will wind down and have some more drinks, and then eventually it's going to be time to go, so we can't stay forever. So what's happening in 2020? Well, you know, it's been crap. But we have a meeting every month, as usual. So hopefully we can keep these in person as long as the general situation stays good-ish. It's always the second Wednesday of every month. If you would like to sponsor, reach out to myself, Stephen, Ignacio. These sponsors are always great hosts, venues. We want to see more of what's around Copenhagen. So even months are generally a kernel of, but that whole schedule's out of whack right now. And odd months, other places also out of whack. So I don't know if there's an odd or an even month. Who cares? Also, we need more talks. We always need more talks. Most people don't feel that the knowledge they have is worth sharing or worthy of a talk, but it almost always is. You become normalized to your own knowledge. So here are some talk ideas. If you know anything about these things, please come talk. If you don't know anything about those things or want to learn, that's also good talk. Or if you know something that we don't know about at all, please reach out. And we have a code of conduct. So generally, be nice or be awesome to each other in the words of Bill and Ted. And everyone should have a good time. We're not the perfect community. People have reached out to us if things are not perfect. But we follow our own code of conduct, so we want to make this a good, safe space for everyone. So feedback too, accessibility, dietary requirements, anything else. We had an elevator. Stephen's beeping. Thank you, Stephen.
Time to start the meeting, apparently.
Okay, good. We should get on that. We're at the end, so hooray, feedback. So do you want to take it over?
Hello, my name is Mikkel. My name is Mikkel. I've been working with Inpay for 14 years, writing Ruby. And even though I've been here for 14 years, this is my first meetup. So I'm totally new to this community. It's super awesome. Inpay is a financial provider, which our CEO will present a little bit more about our vision shortly. But we are actually a couple of Ruby teams here at the office, and we are hiring. So if you know someone that has the skills, then please do come by. We need people. So yeah, and one practical things, as you all know, we have the bar in the back. Feel free to grab anything you like. And at the lunch break, we'll have it in our meeting room, which is in the right corner. Go in, grab your food, and then return back here for social distance. Jacob?
So that was the brains, and I'm the beauty. And remember, there's beer. Actually, it's free beer in the corner. Please drink. So I'm Jacob, CEO and founder. I started programming 37 years ago in the BASIC and assembler. Fortunately, I'm not programming anymore. Otherwise, we would still be a one-man company. We set out many years ago and then said, we believe everybody should have access to the financial system, and basically it should be free, just like email. How come I can send an email to someone in Tonga instantly and for free? But if I want to send money to another country, it's really slow and expensive. So we said, it cannot be that difficult. It's a big opportunity. There are trillions and trillions of dollars moved between countries. So let's create something in Ruby that can handle all the global transactions. Very easy. So what we did was just, okay, let's create, if someone wants to send money from Canada to Australia, in the old days they used the SWIFT system and money moved between a lot of different parties. Our very simple solution, let's create a bank account in every country in the world. Let's put a lot of money in every bank account. So if someone from Canada wants to send money to Australia, they tell the aunt in Australia, what's your account number in Australia? They get the account number, and I would like to send you 100 Australian dollars. Then our system can say, oh, you're from Canada, then you just need to put 117 Canadian dollars into Inpay's account in Canada. The very second we see that money in Canada, we can then contact the bank in Australia and move the funds out. It's very, very simple. So Mikkel started programming. And we decided on Ruby. It's fun, definitely more fun than C or assembler or Perl. You are very productive, and it's relatively easy to see if you make any mistakes. Coming from assembler and C and trying to do pointers to pointers, I know all about mistakes. So and then we've been very fortunate to focus a lot on Ruby. We move about between 1 and 2 billion Danish kroner a month between different countries. So it's actually quite a lot of money that moves around, and if we happen to make a small mistake, it can basically, we go bankrupt immediately. It will take an hour or two. It's quite amazing. So that's why I'm very happy that we use Ruby and not Perl, for instance. So we are just we're building 80 people, 20 nationalities, and just trying to do like the bumblebee. We just continue to try to revolutionize the global banking system. It's a bit harder than we originally thought, but it's great fun. But it's also difficult to explain exactly how do we want to revolutionize the system. What is our dream? The big dream right now is that in 10 years we want to give 100 million people access to the financial system, and how we're doing it is what we will show in the next movie for 4 minutes. I don't know if anyone wants something to drink or eat before that. Otherwise, you need to sit down for 4 minutes and then be amazed. And then it's over to Mikkel after this. And thank you so much for being here and participating.
I have one job.
What if we have sound? Normally we have. So now when you test it, it works. Oh,
I'm Tagman Thompson, and I'm the founder of Tomorrow Group. We have started an initiative to financially include 100 million people over the next 10 years. To understand how, please join me on a journey forward in time.
that's my birthday.
Our journey begins in Africa with Mbali. He owns a shoe repair shop.
Good morning, boys. How are you today?
The business is doing great. Customers are happy and life is good. 8 years ago, Ibali didn't have a business. He didn't have a bank account. In fact, he did not have very much at all. Like nearly 1.7 billion others, he did not have access to basic financial services. To support his family, Ibali had to travel across Africa and was lucky to find a job in a coal mine in South Africa. Every 2 weeks, he went to the local postal office to send most of his salary back home to support his family. But this time, something new happened. When he handed over the cash and presented his ID to send money home, he also got a free entire account together with the receipt for his money transfer. Through his entire account, Ibali got access to Postal Pay, a service that made it easier and cheaper to send money to other postal offices. And when his wife collected the money at her local postal office in their hometown, she also got her own free entire account. Now, Ibali and his wife are connected in the entire network. And because the technology is based on blockchain principles, they can now send money to each other for free. They are also connected to everybody else in the entire network. From the grocer at the local village market to global financial services such as microfinance providers and online shopping sites. Using entire savings, they started their very first savings account. Years later, these savings made it possible for Ibali to return home to his wife to start their new business. Since then, most of the people around them have also joined the entire network, and Entire Pay has become the most popular way to pay in their shoe repair shop. The journey now continues in Myanmar. This is Leon. She has a small successful business selling woven blankets. 5 years ago, a cyclone hit their village. Leon and her daughter lost everything they owned. Thanks to Entire Donate, Leon and her neighbors received a big helping hand from Entire users around the world. The entire network made it possible for people to give aid directly to the ones most in need, instantly and for free. With the help Leon received, she was able to rebuild her life and get to where she is today. Through the entire network, she kept in contact with many of her donors. One of them, an interior decorator, even started importing Leon's designs for her store in Copenhagen. By combining the possibilities of new technology with the reach and trust of postal organizations, we at Tomorrow Group are working hard towards the UN Sustainable Development Goals. We believe financial inclusion is the key to end poverty, support economic empowerment of women, and reduce inequality. Now you might ask yourself, is this just some lofty daydream? No. Today, we are already moving billions of transactions worth billions of dollars for postal organizations and financial institutions worldwide. The challenges ahead are big, but the potential to change the world for the better is far, far bigger. Join our initiative today and let's make a difference for tomorrow.
Woo!
So that's what Ruby can do.
As Jacob said, we have an ambitious plan for building the Tomorrow Group's new payment platform, done in Ruby, parts of it, and a few other languages. I think that's about it I have to say. So I think, oh no, one thing. So under your chairs, you'll find an Inpay flask that you're more than welcome to bring home, and a small gift from us.
Cool.
And now I think Chris, you want to, or Stephen, you want to go?
We have one question from the stream.
Yeah.
Which was, are you hiring remotely?
Not in the Ruby team, we are looking to have on-site people, but in the other teams, I think we are looking into any hire.
Okay, cool.
But any person interested, we have fast track in the EU government to fast track get people to Copenhagen if we are relocating people. And we have with the 20 nationalities, we've done it quite a few times. So
Cool. Thank you.
Thank you.
And we have Stephen coming now.
So I get on with it.
Yeah, get on with it.
I'm going to drag this over there actually just in case. So we need to drag the table.
Okay. Be careful.
Yeah, you guys be careful.
It's your own private one now, isn't it?
Oh yeah. Okay, yeah. Yep. That's good. Can we have another presentation of that? Yeah, that's the one. Okay, right. So, as Chris said in his very generous intro, I've spent a lot of time doing this very pointless project, which was a lot of fun, and I thought I would share it to you. So I want to answer the question, how much fun can you have with a terminal emulator? And how I wanted to answer that question was to make a game. But I'm not a graphic designer. I can't do graphics. I don't know anything about graphics. And the whole point of doing this was to just learn and mess around. So there's no libraries, there's no game engine, like everything is from scratch. So the initial goal was, this was my kind of silly idea. How Wolfenstein 3D. Quite ambitious, but spoiler alert, I didn't finish the whole game. And I said, yeah, I want to do everything myself. And you know, I would like to do some TDD, but yeah, I don't know what I'm doing. So let's see how that works out. So this is Wolfenstein 3D.
It's not yours.
If anyone hasn't seen Wolfenstein 3D before, this is it. You explore a dungeon, I guess. All the walls and the ceiling are the same height. There are doors and things in the map, and you go around and you find keys and you shoot Nazis. All good, wholesome fun. So while it's called Wolfenstein 3D, it's not actually 3D. This is not a 3D game. This is what you call a pseudo 3D game. And that's going to make my job a lot easier, as we'll find out. So there is a kind of a problem if you want to address this in the same way that you would say go about like doing test-driven development on a like web app in Rails. You know, we have lots of established patterns, and we've done it. You know, most of us have done that before at least once. We're doing it at least for the second time, and we know what's going on. But there isn't really a test for this. Because that's what we wanted, right? Like, does my thing respond to the keyboard? You can't hit a keyboard in a test. Does it break my terminal? I don't know if you're a Vim user or if you've had like a bad terminal program exit in a bad state, and then your terminal's just like wrecked, and you have to reset the whole thing. There isn't really a good test for that. Is it fun? Our spec doesn't do fun. So obviously there are like lower level components which are like very TDDable. So we're going to see some stuff with vectors and a lot of kind of like string manipulation and building stuff up. So I'm not going to show loads of test code because it's not that interesting, but yeah, we'll see. It's possible for some of it. So, you know, you're making a game like this. Obviously, you have to start with a level editor, right? Every good first-person game has a level editor. So 2 minutes of vimming later, this is my level editor. So the hashes represent walls. The hashes in the middle are like a pillar in the middle of the room. The X is the starting position for the player, and the G is the goal. So you've basically finished this level if you can make it to the goal, which isn't going to be that challenging. And it's just hard-coded right now. The player is always facing north when it starts. So yeah, cool. We have some levels. So we want to do this kind of like agile-ish. We want to get some results fast. So let's just take our map and we'll just print it out and do some stuff with that. That's not really interesting. That's just catting a text file to the terminal. So maybe we can make the player move around. Maybe we can use like WASD to do that, like real FPS players. Maybe arrow keys to rotate the player. So how hard can that be? Well, okay, so this is that. So we have a really basic terminal application here, which is in raw mode, which we'll talk about raw mode, terminal raw mode in a few minutes. But yeah, so this is an even more basic map. We can see the arrow is the player moving around, and that's kind of an angle, and you can see the input buffer. So I have an input buffer, which is consuming all the keyboard input, and then that keyboard input is being read to alter the game state. So this video is going to look, yeah, out of bounds, yeah, of course, because we haven't done that yet. So we start the game and we go www, so we're going to go forward. And then we're going to go S to go back. And then we're going to strafe, we're going to go D to strafe. A to strafe back. And you can see the player position moving, and you can see the angle changing. So these weird characters, this /E and the open square bracket, these are the escape codes for, well, what we're seeing here is the left and right arrow key. So left and right arrow key are C and D with the escape code in front of them. So yeah, and they arrive in three. If you read a single character at a time, you have to read 3 characters before you consume all of them and have like a valid instruction. So the other thing here is the player angle. So as the arrow keys are pressed, you can see the angle changing. Now, because I'm into user experience, I've made that degrees, and it's degrees from north all the way around. But of course, it's radians really, and that's going to be a real pain in a second. So yeah, we have to handle the display. So what's happening with the display here is it's in raw mode, and what we're doing is every frame, so every key press, we change the game state, reprint the whole thing. We send a terminal code to make the cursor go from here all the way to the top again, and print, and then we send it back to the top again. So we're actually overwriting the same portion of the terminal. If you want to try and clear the screen, you'll find that's too slow. You can only do that about 5 times a second, and we want to do better than that eventually. So terminal input handling. So if you just write, gets and puts, you'll find that your program doesn't receive any input until you hit enter. Again, this is in raw mode, so every character arrives at the application immediately. So we also need a game loop for this, because we have to keep looping. So we have to do some map rendering. So we have our map, but then we have to overlay like all this stuff on it. We need a coordinate system. We need a control scheme. So we just talked a little bit about the control scheme. And we need to track the position and the angle of the player. You also need abundant free time to do all this. So terminal display handling. So this is how you do raw mode in Ruby. You require IO console, and you have a block. And if you use the block version, like when you open a file, it will turn raw mode off for you. If you leave raw mode on and don't put it back, that's what happens when a terminal application breaks your terminal. So you might also want to rescue exceptions in there to make sure that it always does it. But I've left some of the detail out. These are the escape codes that we were talking about. So this is how you make it go to the top left. This is how you save the terminal state and clear the screen. And then this is how you restore. So if you ever used Vim or Less or Top, any of the common terminal apps that kind of go full screen, this is what they actually do. They save your state using these codes, and then after they're done, they put it all back. You'll notice if you scroll back in your terminal scroll buffer, you won't find what you just viewed in Less or Top because it's gone into this other state. So we're also going to use that for kind of cleanness. I don't really understand what this /e is doing. There's loads of different ways of actually typing this out. There's a 4 or 6 digit Unicode escape thing to put it there as well. So I actually did some digging, and the byte value of that is 27. So if you do 27.chr and then turn that into a string, you'll also get the same. I have no idea why it's /e, but it's easier to type /e. So I went with that. Okay. So then this is kind of a snapshot of the middle of the game. You want to say until something that's going to stop the game. You want to get input, update the game state, render the frame, and then restore stuff. You also want to render an initial frame just to kind of get things going. And then the until Control-C is another artifact of using raw mode, because if you put the terminal in raw mode, the terminal won't kill the program when you hit Control-C anymore. Control-C just comes through as a key press. So it's up to you to handle that. So these are the left and right arrows, as we saw before. W walks forward, A strafes left. We've seen all that stuff. You might think, oh, why don't you just get the character and then act on what the character was? Why are we using an input buffer? Well, we need to check if the last 3 of the buffer is ever this, because if we just throw away all the previous characters, then we'll never be able to do that. This is the point in putting my slides together that I started to get bored and looking at what other animations Keynote has. Woo! Consistency is not something I value very highly. So this is how we do the map rendering. So we have the map object, which is just a wrapper around the string that comes out of that file, basically. And then we have a method called overlay, where we say, here's a position and here's an angle. And that converts it into the arrows that you saw. And then we want to extract from that an array of characters that we can print to the screen. And then we're just going to dump those characters into an output buffer. We're going to move the cursor to the top left, and then we're going to dump the output buffer on the screen. So again, you might say, why not just output that straight away? So having an output buffer is really advantageous here, because you can then do kind of like a pipeline, like post-processing. So we get our initial output, then maybe we modify it, then maybe we modify it again. And then you also always know like what was output if you want to respond to that with a hook or something. So we're not doing that here, but that's why having like an input-output buffer kind of model is good. And then, you do need tests for this. It's not that hard to test, but oh my God, like I must have got this wrong 5 or 6 times. I studied physics and I still can't do this. So it's hard. So this all seems like a distraction, right? Because this is still not Wolfenstein 3D, but this is kind of all the stuff we need to get there. So the coordinate system. So here's Lenny. Here's Lenny on the in the grid. So the top left is 0. and then obviously X and Y. So we count Y down and we count X across. That's pretty standard. So all positions in the game are represented by vectors, which is just like a point, you know, like a pair of values, X and Y. We also have to maintain the direction of gaze, so where the player is looking. So Lenny is there, but his position is actually 4.5, 4.5. It's not 4.0, 4.0, and it's not like 4. Yeah, he's not here, he's not here, he's here. And everything in the game is floating point. And then Lenny's angle is 3 pi over 4, and we'll have a look at that here. So the north position would be 0. This is the direction that I'm going to assume he's looking in, and this is kind of 3 pi over 4, 3/4 pi. So pi would be down, and then we would actually go all the way around to 2 pi, which would wrap around 0. And then we have 3 halves pi looking that way. So that's the coordinate system. So now the control scheme. So this is the player, and I've left the probably not the best design decision in retrospect, but the player knows where the player is, and the player knows how fast it can move, and it knows the angle that it's looking at. So if you have the player walk forward, they increment their position by the look unit vector, which is the unit vector in the direction they're looking, and you multiply that by the speed the player is able to move. So a unit vector is a vector in any arbitrary direction with a length of 1. So because the length is 1, we can multiply it by a speed, and we have something that makes sense. You can see when we turn left, we have a turn rate, which is kind of off the initialized here because I just made it too long, and I wanted some convenience here. We also have a turn rate. So if you turn left, you reduce your angle. If you turn right, you increase your angle. If you turn all the way around, then you're coming up to 2 pi. You cross the boundary at 2 pi, and at that point, 2 pi has to become 0 again. So we do modulus with 2 pi to make that wrap around. So we also have a vector class, and we need to be able to create a unit vector from any angle, because it's the angle we're tracking. We're not tracking the unit vector as the player moves around, because that's relatively difficult compared to just incrementing a number, which is the angle. So this is how we take an angle and create a unit vector from it. So yeah, some high school maths, not too bad. So then we have a right unit vector, a left unit vector, and the look unit vector. So the look unit vector just uses the angle. The left unit vector is the normal to that, which is half a pi that way. The right unit vector is half a pi that way. And then we just add these and subtract them as necessary. So that's cool. We don't even have a game yet. We've done all this stuff, and we're still not really very far. So this is where we want to get to. This is a demo of a ray tracing pseudo 3D Wolfenstein-like environment. Like I said, it's pseudo 3D because we just actually have a 2D plane, and we're just making up this 3D image. We don't actually have any 3D models or anything like that. So as the player turns around, the player has a field of view, and we have to calculate what is in that field of view and make some kind of image. What's maybe, if you're interested in this or you know about this, the graphics on the left have something called fisheye correction, because if you look at a wall, the point that's directly in front of you on the wall is closer than the point that's there. So what happens is when you approach a wall, the wall starts to look slightly curved. I didn't correct for that, but that's just so you can feel some of my pain. This is what we're dealing with. So we know where the player is, and we know where the player is looking. We have a map which tells us where the walls are, and walls are actually everything that's in the game. So great. So now we have to draw the scene. So given your field of view is 90 degrees or half pi, that's what we're going to try first. We have to print this to your terminal. So your terminal could look, vaguely like this. It could be 80 characters wide. It could be 40 characters high. And what we're going to do is we're going to sweep from left to right. This is going to be the player's looking angle minus a quarter pi, minus negative 0, and plus a quarter pi over there. And as we saw in the animated GIF, we have to draw a line, a virtual line, from where the player is along that angle, and we have to keep going until we hit a wall. And then for the next increment of the angle, we do the same. Then we increment again, and we do the same, and we do the same. And we do one of those for every column in the terminal. So this will run on any size terminal within reason. I'm sure you could push the limits of that, but let's say it was 120 characters wide. It would cast 120 rays, one after the other, from left to right, and it would get back 120 measurements of how far away things were. And then, for example, we could use ASCII art style thing to put a hash to say that something is there, and we could have a space to say nothing is there. So that's kind of where we're going to start. So this is a ray tracer. This is the whole ray tracer. There's two questions that you might want to ask it. One is what is the distance to a wall from given this map from this position and looking in this angle. And then the other thing you might want is the wall position. And you need the position of the wall to find the distance, but sometimes you just want the wall position. So what we do here is we clone the input position because we may want to mutate that. We figure out the unit vector that the player is looking in, and then we increment it by the resolution. And then we have this tight loop here where ray equals ray plus the increment. So we start here in this direction, and we add this much, and then we add this much, and we add this much, and we add this much. And then eventually we hit a wall. And this map wall method is just indexing into the array of characters from the text file, and it's just saying, is this a hash or is this a space? Is this a hash? And that's how we decide where the walls are. And that's it. It's surprising how simple that part is. Now we have to render it. This is getting a little tricky now. So I have an ANSI terminal renderer, and we have a gradient. So I stole this from an ASCII art website. This string of characters goes from kind of low brightness or low intensity, or the opposite, whichever way, to high. So in theory, you can use these to create something that goes from light to dark or dark to light. So that's what we're going to base it on. We have a scene that we're trying to make, and as I said, we're going to do this column by column in the terminal, and we do it for the range of field of view. Then for each angle in the range of field of view, we measure the distance, and then we have render column. How hard could that be? Seems fine. So the field of view range is basically just saying, okay, we have a leftmost and a rightmost angle, and we want to step through them at some interval. And the column arc width is the width of your canvas minus 1 with the the field of view divided by the width of your terminal, basically. And then half of the field is to the left and half is to the right. So that's that's the range object that we're iterating over. So then rendering the column. So we render the column because everything at this column is going to be at the same distance. We just care how far away the wall is. And that's the only thing we care about. So we do it column by column. And then I don't know if you noticed, the last line in this function is to transpose. So we do it column by column. And so if you wrote out the arrays, the columns would be this way. And then we just transpose it that way before we print it. Rendering a column, there's some complications. We know that each column has some amount of wall that we can see, and I can see some amount of ceiling, and I can see some amount of floor, and we have to decide in what proportion that happens given a distance. So we have a ceiling projection, which is the proportion, and then we calculate the sizes. Now the ceiling and the floor are always going to be the same, and then the wall is always going to be in the middle, and the eye is always, so I'm actually this tall. I'm doing Wolfenstein-like about this tall, in the middle of the wall. And then the ceiling character is just going to be a space, so we're just not going to bother having a ceiling. It's going to be like an open environment for now. The floor, I'm not going to get too complicated either. I'm just going to always print a dot. And then what I'm going to do is for the wall, I'm going to vary the character that I use using that gradient based on the distance. So yeah, how much thing? I think I spoiled all this. So let's do some maths. So so the appearance, the apparent size of an object falls off as 1 over x. So 1 over x is the green line. But what we want to do is take a distance and figure out a size. And we would really like it to start at 1 and go down to 0. I don't, if you remember some high school maths, you know that if you multiply one side by 2, you can stretch the graph this way. And it just so happened that 2x, which was one of the first things I tried, is kind of actually perfect. It goes straight through 1, 1. Because if you're really up against the wall, if the wall is in your face, you're only going to see wall. So if you're 1 unit away, I want the whole view to be wall, which is what we get at 1, 1. And then as you get further away, it kind of falls off. And these arrows are supposed to have labels. Oh, here we go. So when you're close, it's, oh, sorry, not 1, 2. 2, sorry, 2. 2 is going to be my limit. So at 2 units away from the wall, you're going to see all wall, and then you're going to start to see ceiling and floor as you walk back. And then you want almost no wall when you're far away. And then you have to be aware of infinite wall. No, you don't want infinite wall. That can be bad. So this is how we do that. So this is our this is 2 over x, right? But we really need a non-zero distance to prevent infinite wall. So the minimum distance is going to be 2, as in that curve it hits a value of 1, which means entirely wall at 2. So we just want the maximum of these. If this distance is 0, then we still just use 2 because we get 1 out of the calculation. So the wall projection kind of makes sense to me, and I tried to just use that, but it's really hard. Because the ceiling and the floor have to be the same, it's much easier to divvy up your array based on the ceiling projection rather than the wall projection, because you can say, okay, I want like 10 of these characters and 10 of these characters, and then whatever is left in the wall. If you do it the other way, maybe you can do it. I couldn't do it. It was really annoying. So I made a ceiling projection, which is the inverse of the wall projection. So yeah, I at the horizon, ceiling and wall size are equal. Yeah, we want to go from 0 wall to entirely wall. I kind of spoiled all this. I should have paced myself. So ASCII art's cool, right? So we know how big we want the wall to be, and we know that that's going to be a 1/, distance relationship. We also need to use our gradient scale to decide how bright it is. So brightness falls off as 1/r². We use the gradient. So we just simply calculate the brightness from the distance and map it to the array index within the bounds. Easy, right? Still no game. So this is pretty mathematical. This is cool. So I started with 1/x². And yeah, so by adding and multiplying x, essentially, I've basically harangued this function to do what I want. So yeah, you can still see it's basically a 1/x², but we add 1, and then this 10, which looks arbitrary, is actually the max depth in our game. So if something is 10 units of distance away, we're just going to say you can't see that far, like it's too dark. So yeah, the cool thing about and 10/2, I don't know why it's 10/2, it just works.
The answer is 5.
I think. No, it's 10/2. You can always justify multiplying or dividing by 2. You don't have to justify that. But, so we've got the max depth. It's 10/2. So as you can see, when you get over to 10, by 8, basically, this has fallen off to nothing. So this is roughly what we want. So we're going to use that. So how do we decide the wall character? So that if it's greater than max depth, we don't care. Too far away, no character for you. So we saw a gradient before, but now we see something called wall gradient. And is that something cool? Yes, it's something cool. We're about to see that. Yeah, so intensity is the formula from the Desmos screenshot that we just saw. There is one tiny difference here. Instead of using x divided by something plus 1, we use plus 1.01. And the reason for that is we never want the distance to be, we never want the brightness calculation to be calculated based on 0. And that just makes it much easier to fit it within the array bounds. So we just add a 0.1 on the end just to make sure that it's never 1/1 giving you 1. We want it to be 0.9 something. So when we do the floor, imagine this is 10. When we floor, we want to get the 9th element. We don't want a 10th element, because otherwise we'd have a 10th element that would basically never be used. It would only be a special case when the distance was 0, and that's not really what we're doing. So yeah, a little tweak there. So, oh, that was disappointing. Can we play? Oh. Oh dear. Okay, if I find my pointer, I can show you this video. Yeah, my skills don't really involve Keynote. So yeah, here's like a very rough version of that. So we see some walls and some, over there looks dark. Let's investigate over there. And then, a wall is appearing and getting brighter and getting bigger. Yeah, cool. We win. We found the goal. So yeah, that looks kind of crap, unfortunately. But it's almost recognizable. So what we'll do is we'll take our gradient characters and we'll make something a bit more interesting. So if we use some of the escape codes, we can make the characters print red. So we'll have at the darkest first, we will just take those characters and we will print them red. Then in the middle, we'll reverse them and we'll print them black on red, and then we'll finish with a black on red space, which will be a fully red block. And then we also want to be able to have the tile, which is our goal, to be recognizable. So we'll just do the exact same thing in green. So yeah, those colors will help out nicely. So yeah, we have some other issues to address. This is single-threaded, which you may or may not think is a problem, but there are some limitations. And just like the first version of the game, which was just a flat map that was printed, it only responds to get input, and then it re-renders. So it's very kind of like 8-bit microcomputer, like 80s style. You press a key and the screen changes. You press a key, it changes again. And it's really kind of jerky and not really what Wolfenstein 3D is about. So we can fix that by taking the input and updating the game state in a separate thread. Now we can do both of these together because it's actually super quick to do that. What's actually time consuming is all the ray casting and deciding what character goes where and then outputting it. So we should be able to update the game state in a separate thread independently of the printing, so that, for example, you could turn or move at a constant rate. And if you can't calculate the frames fast enough, then you just drop frames, which is, roughly how I think modern games work. Oh dear, what happened here? And yeah, it's not very challenging without Nazis. Like, it was kind of fun to shoot Nazis. But as you can see, it's taken us quite a while to get here. So we're probably not going to get to Nazis today. So instead, how about we just make it super hard to find where the goal is? That could be fun. Oh no, my slides. And then performance. So it'd be cool if it could run 60 frames a second. It won't, but it could. So I have another video which Keynote doesn't want to play. Let's try this. So yeah, remember how we started facing north? Like, I really should have thought of that when I drew this map. Just facing a wall. Here we go. Wow. Running down the corridor. The wall. I think the turn rate is a bit fast, but this is one of the issues with these things. You just have to endlessly fiddle with it until it kind of like feels good.
It's a fast-paced game.
One of the other issues with the terminal input, so even in raw mode, every character press will be received immediately. But you can hold W down to run forward and it will key repeat. But as soon as you hit an arrow key or you want to strafe, your key repeat ends. That's why I'm kind of like bursting forward and then kind of bursting forward again. Because you can't press more than one key at once, and you can't key repeat smoothly with multiple keys. Well, unless your keyboard settings are sufficiently modified. So yeah, this is, where are we? This is hard. So I left the map there just because it is really difficult, but I did add a key to hide the map if you want to be really like, if you really want to challenge yourself. I kind of got lost again. Where are we? Oh, okay, we're here. But we have to go all the way down here. It's going to take forever.
Can you in fact walk through walls?
No, there is a bounds check which stops you walking into walls. But yeah, almost looks like a maze, right? Some kind of dungeon. And it's kind of nice to see the kind of very claustrophobic, like narrow corridors, and then kind of opens up into bigger spaces. And then yeah, you find like lots of dead ends. And
I'm amazed the ASCII gradient works so well.
Yeah.
To know what you want it to do.
It's very impressive.
It's very cool.
thanks. I'm kind of like showing you this today. I'm like, are they gonna get it?
That's not Wolfenstein.
That's it.
Well, when you have two more units of work, then it's complete.
Yeah.
Don't show this to your family at Christmas, but we love it.
Yeah, I've been staring at these shapes for so long. It's like, do other people see the way I see? I don't know. Hey! Cool. Woo! So yeah, maybe the last interesting thing, unless you wanted to see more code, is the performance. So that was hitting a peak of about 40 frames a second, and that wasn't the first version. So this is using RubyProf to profile what's going on. So this is tracking every method call. It's telling us how long. This is a different demonstration run. But yeah, this is how long in total it's spent in the vector plus method. And then yeah, you can see how many calls. Like there's a quarter of in a short game that was less than 7 seconds, there was 250,000 vector additions. And yeah, so just looking at this, it's pretty obvious how. Well, if you're into optimization performance optimization, it's relatively clear how to make a big dent in this. So Vector Plus, the standard library Ruby vector class is immutable. So as soon as you call plus, it creates a new vector and returns it. That's a memory allocation. So memory allocations are one of the slowest things you can do. You do not want to perform memory allocations if you can afford it. It's also doing a collect and a size. And yeah, if you look at the documentation, the Ruby vector is an n-sized vector. So it's not really optimized for just dealing with X and Y. So it's doing like array allocations, and it's immutable, so it's always creating new ones. And yeah, you can see actually based on when you actually want the vector class, you require matrix. So it's really just kind of a general purpose object and not really suitable for what we're doing. So I re-implemented vector, which was easier than it sounds. And then we have this, which is like much more reasonable. So we spend most of our time asking the map if there's a wall there, which is understandable, and we do that almost 1 million times because every frame requires a bunch of rays to come out, and each one has to ask if it's in a wall yet. I also introduced mutable vector. So a mutable vector, when you add to it, just mutates its internal state, so it doesn't allocate any extra memory. And I adapted the small ray tracer code you saw to do that, and that is way faster. And then we can see that this is actually indexing into a vector, and yeah, rendering a column and IO right. So these are the kind of things that we expect to be bottlenecked on. And that's all I have.
So no tests whatsoever.
Yeah, do you want to see some tests?
Yes.
oh, this is awful now. Oh my god. Okay, maybe I can do it like this. Okay, so this is the game. Some of the code samples I showed you were from kind of incremental points along the way. This is how the game turned out. Turns out that when you're doing so much in the terminal, you can't really do puts anymore, so we need to do that to a log file. Yeah, that kind of thing. So our spec. What's in our spec folder? We have a map spec. Okay, so this, oh no, map. Spec. It's not too much to ask, is it? Come on. So yeah, we have a fixture for the map, which I kind of like to put out of the way because I want you to see what the behavior is. And this is the fixture for the map that we're using in most of these tests. So yeah, so it's very important to check if something is in bounds. Maybe I can show the fixture to the side. Is it because I'm typing at a weird angle that I can't do anything, or is it because it's so big? I don't know. Maybe this will work. Yeah, okay, maybe that's the best I can do for the moment. So, yeah, 1.0, 1.0 is right on this corner, and it should be in bounds, and 7.9, 3.9, which is 1, 2, 3, is right here. That should also be in bounds. So we check the bounds. Yeah, we return a 2D array. We produce a string output. The player start position is found in the middle of the X character, as I said before. And then when we overlay the player, we don't mutate an existing map, we return a new one, and we expect the arrows to be put in based on the angle. So what else should we show? Spec. Yeah, the vector spec. The vectors are actually, let me show you the implementation first. Mutable vector, so it's just like a point class almost. It's castable to a regular vector. It has a magnitude, which is just doing some Pythagoras. It has an equals method, a plus method, a minus method, and that's all really. So the spec is relatively straightforward as well. We can index into the vector. We can compare it to other vectors. We can figure out its magnitude. I'm a nerd, so I know a triangle with sides 3, 4, 5 kind of work in Pythagoras. Yeah, we can add, we can subtract. What's nice about objects that do mutating things to themselves is if they just do that and don't give you any information back, like command query kind of separation. So we do that just by returning self, rather than nil, or just, maybe we could just write the plus, like the line that does the addition, but then we would we be returning X or Y? So yeah, that's kind of arbitrary. So I thought self would be a better thing to return. And then you can also multiply. So we just take a vector, we multiply it by 3, no problem. And that also returns self. What's kind of difficult to test is the rendering. So if we look at the rendering, let's get rid of that. So yeah, one kind of strange thing about doing this in Ruby is you obviously want to put complex functionality into classes because Ruby is good at classes, but really, like, there shouldn't be any state in this. This is actually just a function. So I actually use, I just use a dumb trick here just to make my class into a function. The thing that I want to I have the tracer like very early in the process, and then I want to give all the other stuff later. So I just use this little trick here to make it into a function. And I actually have an early version where I just spiked some stuff out to figure out how to do this, where I did just use functions for this. Unfortunately, the functions get big and then they get hard to test. And so this seems like the Ruby way to do it. So yeah, how are we going to test this? So if we mock the map and say whether wall is true or false and whether goal is true or false, then we can kind of manipulate the distances effectively, and then we're going to fake the wall position, and that comes back from the we're going to fake the tracer and fake the wall position because all of the rendering is based on the wall position, and we don't want to take a whole scene and like match that against a fixture because that error message would be so unhelpful. But I wouldn't know what to do with it. So we just kind of test one column at a time with a specific distance, yeah, that's the main kind of test approach here. So it traces the wall distance column. So we expect the tracer to have received wall position exactly canvas width times. That sentence isn't very good, is it? I need to rewrite that. So that just means if it's 80 wide, we expect it to have traced 80 rows. So that's not like a very strong test, but like I think my alternative would be not great. So that's kind of where I started. And then we have a bit more of an involved test here where I capture all of the angles that are fed into the ray tracer. And I'm just going to check the first one is minus a quarter pi and the last one is plus a quarter pi, and that there was 80 of them in between. Like that's good enough. We test for confidence, right? Not for rules lawyers. So
time.
Yeah, should we stop?
Wrap up.
Cool. Okay. And then yeah, so the other thing we do is we render a scene, take a column from it, and say like how many walls, how many floor characters, and that's it. Yeah. So that's. I will post the repo later.
Thank you, Stephen. What an incredible waste of time. I can't imagine doing that. But slides.
Thank you.
Oh, I don't know. I won't think about it.
So you'll be accepting pull requests and continuing to maintain this.
Of course. Yeah.
Okay.
Yeah.
Cool.
Send me some Nazis.
Some Nazi. That's the next pull request. Cool. So thanks for the awesome talk. It was cool. I think we have some food now. Time for more drinks. Break, and then Ignacio will be up in maybe 15-20 minutes. So we'll get started. Are you going now?
Oh, yes, it did.
I think I can make it there. I mean, my life bar will probably crash very quickly, so then you don't be sorry. Do you have the Wi-Fi? You can ask. Where's Skype? My connect. Okay. How long did you actually spend?
Years ago, this what?
Never seen you.
Yeah, that might actually be real, like, if you
You don't want to bring it up?
Yes,
But one can you study exercise and you had any okay?
I don't want to say I wanted to.
Yeah, the theory around ray tracing is quite interesting.
Yes,
It's very cool.
Chris, how come it's
Yeah, I thought about that as well, but it must be on purpose.
It's not. I think it's to give you instant feedback with no processing. It isn't flooding when you view it. I don't know. This is the first time I've done it.
You?
No.
Ready to go, Ignacio?
Yes, yes, we are about to start.
This is my magic again.
Hello everyone, thank you for coming here today to this meetup. My name is Ignacio and I will talk today about the topic called Kubernetes, which is a new cool word. You might have heard about it. It seems to be popular in some circles. And I work usually as a developer / manager, and I'm not a sysops guy. I like Linux, I love my Linux, and I know how to manage a server, but I'm not an expert on the topic. But I've been forced to interact with Kubernetes because it has come in one past project and my current project, where we hired an external company to manage everything related to servers, and it was decided that we would use Kubernetes cluster to run everything. And recently, I got very angry at it because basically we had production downtime, and the people responsible for it didn't respond, let's say, in time or thoroughly enough. So I had to jump in and try to understand what was going on, and that led me to learn a bit more about Kubernetes. And I would like to share something with you. So we have a few slides about what it is and what it does, and then a bit of a live demo. I'm sure something will break. But we can at least give it a try and see how it works. Let's just move ahead. So what is Kubernetes? An open source container, that is like the official definition. Open source container orchestration system for automating computer application deployment, scaling, and management. Well, it's something for deploying applications, usually web applications, and it was written in Go by people working for Google. And it's actually coming from a preview. Basically, they tried to extract a simplified version of what Google was using to deploy thousands of servers and to manage thousands of servers into big, let's say, virtual computers. And this is supposed to be the simplified version, but you will see it still has a lot of depth and a huge amount of components moving here. It's like an easy definition. It's just a way of stitching together a collection of machines into basically a big computer. So instead of having 10 servers, you have one big pseudo server that acts and behaves as one machine. And it can be, if you use something like Docker Swarm, basically if you are running Docker containers on groups, it's basically a replacement. You can just consider it a replacement of Docker Swarm. So what can you use it for? You can join together Linux servers into clusters. It might support other systems, but I've never seen it, so I'm going to say Linux servers. I guess that's the most typical use. It runs Docker containers. You've probably played with Docker. It's a way of isolating your code and your applications and your software into small packages that you can then share around, download, push to repositories, and execute in other servers. It's very efficient because it uses something called like Linux containers, a feature of Linux, to isolate things without creating a complete virtual machine. And that's Docker. So basically, it's just a wrapper on top of Docker run on Docker. It just installs Docker on all the servers, and then it runs containers on them and kills them and restarts. That's what Kubernetes does in few words. It also comes with things like load balancing, scaling, and rolling updates. So you can deploy the new versions of your application easily, and you can scale with new servers, and you can use like very advanced load balancing. And a bunch of other features, but that's the summary. Some terminology, probably a bit small, but let me just read it aloud for you. Cluster is a series of servers connected together and sharing resources. So you have 3 physical servers or virtual servers. You put them together, it's a cluster. A node is each of those servers in the cluster. They typically run Linux and Docker, and you can have master and worker nodes. A master node will basically take decisions on what to do, like what to start, which resources to assign to where, and the worker node will just run whatever load it has received. It's actually non-true because in many of the smaller Kubernetes clusters, you will have master nodes also running worker jobs. So basically, a master node can also do the worker part if necessary. But it's designed to separate the master nodes and the worker nodes. Then you have pods. A pod is each of the Docker containers that are executed in the nodes. A single pod can actually have multiple Docker containers, but that's overcomplication. But in general, you might have a Rails app and 3 servers, and you might have 2 copies of the Rails app in each of the servers. So you might have 6 pods, which are basically clones working together, and Kubernetes will load balance them and pass the effort between them. So each of the copies of your application, let's say, would be a pod. That's a running application. And etcd. If you've played with Linux, etc is where you store all your configuration. So etcd is just that data store of the cluster. So this is where all the configuration is stored. So the master servers keep a copy of that, and if you have multiple master servers, they will have like a shared data store between them. So it's supposed to be consistent and highly available. It's a key value store, and it persists. It knows about the cluster. So basically, if you plug out one of the servers, if you have another master server, it should keep a healthy copy of the etcd. And if you have 2 of them, they will try to negotiate which is the right one. So yeah, that's how it stores data. So a lot of the configuration for Kubernetes, you will see a lot of these YAML files. It's a bit hard to read, but basically, so there are these YAML files where you start with something called the deployment up there. Then you have something called the replica set. Then you have the pod, and then you have the containers. In general, each deployment refers to an application, and you have configuration like how many copies of this app you need. Maybe you just need 1 database and 5 Rails applications and 2 sidekick workers, for example. So you can define how many replicas you want for each of your deployments. And then when you're talking about containers, you can basically pass what Docker image you want to run, and then other settings like ports. Not some here, but there are a million other settings you can add, like limits or how many resources do you want. They are long and hard to read, and there are tools to help you deal with these YAML files. In the end, you just run in your terminal, and you run kubectl, which is the CLI tool for Kubernetes, and you apply these YAML files. But it's very typical to use a tool in front of this, like Helm, for managing your servers, but it's not strictly necessary. But let's a few useful kubectl commands, so you can list the pods to see everything that's running in your cluster. You can basically open if you want to like SSH into your application, very typical. You want to open a Rails console or play with it. You can basically take the name of your pod. If you run my app does, and then you get a random number that Kubernetes will add. That's the name of your pod, and then you can exec/bin/bash on it, which is the same thing as opening SSH connection. Let's say it's similar to how you open how you enter a Docker container locally. And then there's some commands for scaling, which is typical, changing the number of replicas you have on your app, the number of copies you want to run, and you can also get some stats like kubectl top node. There are a million commands. This is just a few commands that I use when I'm working, and they thought might be interesting to look at. But the next part of my talk, before I go into a bit of a life experience, is some bad experiences. So that's where I came from, how I got angry with Kubernetes, and why we had downtime. So let's take a look at, well, this is super small, but I can give you some pointers. This is an incomplete list of all the different Docker containers running in our cluster. So a lot of things. On the top, and they are ordered by RAM usage. On the top, we have a couple of Elasticsearch instances, each of them taking more than 1 gigabyte, 1,300 megabytes of RAM. They are hungry. Then we have an instance of our application. It's almost 1 gigabyte. something called the process engine, which is Java tool we use, Camunda tool for managing processes. When we have multiple copies of those, Keycloak for ours. So a cluster can hold, in the end, when it grows, a huge amount of pods. And you need to start taking care of that when and your resources. And this is just our three. We are running on production with 3 servers. They all have 8 gigabytes of memory, and this is the current usage: 72, 86, and 63%. So you would look at this and say, okay, it's this is the CPU usage. It seems like they are being used, but nothing too critical at the moment. And these 3 servers will run all of the different containers, and Kubernetes will decide where it should run its thing. So the number one issue we have experienced, like in the past project and the current one, is out-of-memory issues. So basically, it tends to be curiously easy to run out of memory on a Kubernetes setup. And why is this? If you misconfigure your cluster, Kubernetes does not know which pod should go into which node. Basically, we just start throwing them around. Okay, here a couple of them, another one, 3 here. And it's easy to get randomly all the heavy pods, like all the Elasticsearch instances or the heavy Rails instances with a lot of RAM usage, into the same node, while another node is just waiting at 30% RAM usage, just handling things like monitoring or log pods, like it's very small non-critical things. So it can happen by chance that it works, and then after a deployment, something gets into the wrong node. And if you are running at 80% RAM usage and you basically put a few of the heavy ones in the same place, you will run out of memory. And basically what happens is at first it tries to kill some of the pods, but if the whole system runs out of memory, like the whole node, it will become unavailable. So the cluster will say, hey, everything else, go to the other nodes. And if you only have 2 nodes, then it's like a cascade of errors. You start seeing things go wrong. Oh, I'm getting a message. Oh, one of our nodes is not available. Oh, our app is still working. 2 minutes later, the whole thing goes down. So it can cascade very quickly if you don't configure it properly. That means letting Kubernetes know about each of your applications, like what's the typical RAM usage, how many resources it should have, what it should do when we're getting close to the limit of memory limit, because by default, it will just use memory, then start killing, and basically it will most probably crash the whole thing. And it takes some time to recover from there. And yeah, it also comes with a feature of rolling deployments, which is very nice by default. So whenever you say, oh, there's a new image, a new Docker image, what does it do is if you have like 2 instances of Rails, for example, it creates a 3rd one with the new version. It waits until it has initialized. Maybe you have some health check, waiting until it's completely running. And then when it's running, it will stop one of the old ones, and then once it's stopped, create a new one. But that means that at some point you're going to have like a 30% extra usage because you have more pods running for the rolling deployment. So that's another reason not to be too close to the edge and to manage your RAM. And the third is it can happen that one of your nodes goes down. For example, in our setup, it was decided that we would have each node on a different data center. That means that it should be more reliable, but it also means that the chances of downtime are 3 times. Because if any of those data centers goes down, one of our nodes will go down. So it multiplies also your chances of some issues if your cluster doesn't have enough resources and space to handle losing one of your servers. So that's what happened. Too much, I'm sorry to say. So yeah, be careful with that. Yeah, this is our sysops team saying, hey, AWS offers in the same zone what they call the 3 availability zones, which are basically 3 data centers. This is in London, different places in London where they have a lot of servers. And the idea was, oh, let's put each of the servers in one different place. Well, yeah, the concept is good, but careful with this. If you don't configure it well, it can come back to you. For example, one of our microservices uses MongoDB as and it needs persistence. So it needs to be stored somewhere safely. And the most efficient way to do it in AWS is to use Elastic Block Store. But Elastic Block Store does not work across data centers. So what do? You have to tell Kubernetes, hey, I'm sorry, but this pod, you can only write on this node. So then you have a complete dependency on that particular server. That thing cannot be moved to the other servers. And yeah, if you are stuck there, you have a dependency, you can't shut down that server. You start getting a lot of complexity. So data storage across data centers is just hard, even across servers. For example, if you use like a hosted database, that usually works best. Like AWS offers, these PostgreSQL instances that we use for our main DB. Those work great. But if you start having like things like MongoDB and you need to store it locally, then it can become messy very quickly. And yeah, the third issue is that if you have something which is single-threaded and it has to run only once, like you can't really scale it in parallel, because it's a Node.js process that you can't run two of them because they access the same thing, and you can't run two of them in parallel, then be very careful again, because you need to shut them down properly before starting a new instance. If you basically start two of them at the same time, you can enter a race condition, which was happening here now with a Java software that was designed only to run by itself. And two of them were being started, and every 6 minutes, one of them was killing each other, and then it was being restarted. So we had like 20 seconds of downtime every 6 minutes for like the whole day. See, we realized at almost 9, like what was going on, and that was our peak in RAM usage. Like, oh, something started, oh, dies, and something started. So that was a big mess also. So yeah, Kubernetes is great, but you need to spend a lot of time configuring. That's the thing that what I learned. And if you don't, then you might encounter a lot of trouble. Demo time. So I have here my instructions in paper. Let's play this to some live CSOP stuff. Yeah, no, thank you. No, that's demo time. Okay, so I have a couple of servers, and they are in different cities.
Take them down. Take them down.
We're going to do that. We're going to check it if what happens. So, but I just installed Kubernetes on them, and nothing else. I basically deleted everything else after my testing. So they just plain two nodes with Ubuntu, install Kubernetes, and connected them together, following the instructions. It takes a step of work, but they should work as a cluster. So let's SSH into one of them. So SSH root. So this one is in Helsinki. And I'm going to take a look at the cluster, just kubectl get pods, no resources, there's nothing there, it's just empty. And what I'm also going to do get nodes. So we have a couple of nodes, they are ready, both have a master role, which means they are ready to, they are responsible for the cluster. So if one of them dies, the other one should take over and decide what to do. And we're going to try to deploy a Ruby Rails application here. So if I remember correctly, let's do.
Create.
Exactly. Exactly. So kubectl, create deployment, a name, and then the image, which is now stored in Docker Hub, Rails demo for Docker. So it's just a simple Rails app. Let's look at the app later. So I have created a deployment. So now if I do get pods, now there's one pod running. Okay, so basically it's been executed, and the next thing is I need to create a way to connect to that service. So sorry, create service. Yes, so it's running in development mode on port 3000 because I designed it to be like a slow app, because I just want to find something slow that we can try to stress a bit, and with a bit of lag we can see like how many requests per second we can get, and if we can scale a bit our cluster. So now we should have a connection to this. What else do I need to do? Yes, I need to now get services. So this will give us like a random port. I'm using like the minimum amount of steps to deploy something in Kubernetes. You can make a load balancer and much more complicated, and an ingress controller and complicated stuff. But it's the minimum, just a deployment, which will start the Docker container, and just a service that will allow you to connect it from the internet. So here we have the port. So I'm just going to copy this because it's random. There's a way to make it not random, but I didn't get to that. So I want to try to see if we can go there. Yeah, you're right. Okay, so we have the app running, and it has some cool features like a to-dos list that also generates the first 10,000 digits of pi. That's my way of enforcing a bit of CPU time. I guess it's like almost a second in the current servers. So basically, if I reload this page, just takes like around a second, a bit less, and just it generates it again.
Shout out for hi.
Yeah, great.
It's like you can't even see the last one. I know that. Not right.
Yeah, there's a lot of scroll here, so you can check. Yeah, 10,000. I was playing with the numbers to see like how long to find a reasonable number, and this one seemed to work. So now we're going to try to stress this app. So I'm going to connect to a different server, like that where I host my website and few other stuff, and I'm going to use a tool called Siege. Maybe you have seen it. And I just need to pass the right port. And yes, just 10 seconds. Well, let me make it bigger. So this it will basically query that URL for 10 seconds, and just it's the minus benchmark mode, so it will not wait anything. It will just throw. I think it starts with by default with 25 workers, just asking that URL until the server dies. That's what it does. So that should be 10 seconds. Let's see what happens. So here it's our cluster responding. It's not very fast, but it's responding. And it was able to do 1.6 transactions per second, because we had like 15 hits in around 10 seconds. So let's scale this, because this is slow. We need more speed. So I'm going back to my cluster, and I'm going to do scale it. Let's start with 2. And now if I do get pods, now we have a second one, which is only 3 seconds. Of waits, and the other one which has been running for 3 minutes. And let's try again. Let's try to stress it again. Let's see how far we can go. Okay, so now we got 31 hits. We are at 3.2 transactions per second. But let's see how much we can push it, because our 2 servers, Helsinki and Nuremberg, are called. They actually can have two virtual CPUs each. So we should be able to at least do 4 of these, and we should get an improvement there. And that's how easy it is to like create new scale when you have the cluster running. You are just consuming more RAM. But I think we should be fine. If I do like top and M, you see we have one Ruby process, but it's not we have a lot of free RAM. No, we are fine with RAM. Our bottleneck here is going to be the CPU for sure. And if you do a Docker PS, well, there's a lot of crap here, but that a lot of crap is a lot of pods created by Kubernetes, so it's just running Docker. But some of them, they must be our real stuff. Wait, let me clean it up. Yeah. So have Rails them for Docker. We have I think this is a couple of. So in this particular node, we have a couple of them. They always have like 2 instances. One is the proper one, and the other one is just something internal for Kubernetes. So we have a couple of copies here and a couple of copies on the other server. Okay. So now that this is running, we're going to try to stress it again. Let's see how far we can get. Okay, so we got at almost 7 transactions per second. That's I think close to the limit of our 2 servers. If I run it again, because some of those apps have yet started and the first request is a bit slower, I think we can probably get to 7.7 transactions per second. Okay.
One more time.
Yeah, but now we're going to do it with double it. So let's just stress it a bit more. Let's see if how good this app scales. So now we're creating 8 of them. So 4 of them are being created, and in a few seconds, they are running. Okay, so just to see if there's an improvement on the throughput. 5.3. So we have actually gone down because we have to switch more between jobs, and probably some of these apps were not ready first time. So I think we are actually losing some performance if we scale too much. Well, 7.8. The second time was okay, but basically it's the same. There's not a big difference. We can continue adding more pods, but it will not make the pi calculation faster. It will just serve the load a bit more, but that's it. So, and the next thing I want to take a look at is I want to kill one of the servers. So I'm going to connect to the others. So I'm going to divide my terminal. So this is in Helsinki, and I'm going to connect to the other one. So I think it was root at .huerta.net. Hopefully, yes. Okay. So this is also running. So if I do a top you can see all the Ruby instances running also in this one. So below we have a Nuremberg, and on top we have Helsinki. And I'm just going to reboot the server while I'm doing a bit of let's try to see if we can do it on the same screen. Give me a second. So I'm going to log out here. Copy the command. Good. Okay. Okay, so I'm going to start running this, and I'm going to reboot one server in the middle. It should start going slower, but Kubernetes should be smart enough to say, oh, something's wrong. Okay, it seems like nothing started, or now we're getting a few errors, socket errors, but it's still returning a few of them. In a few seconds, it should start realizing, hey, something's wrong with the other server. We should, pass the load to the other one. Now it's refusing to connect. Cool. Yeah, that's great. But if I go to the app, if I roll with my browser, it's still running actually. So I think sometimes it gets cast on the DNS because I'm using a DNS load balancer. But the app is still running, even if the second server is not there. Let's try again. Let's see if we can get it to run with seed. No, it's just refusing to connect right now. Yeah, but we can't resolve. But the app is still live. You can still connect with your browser and see a lot of versions of Pi. Just going to try a few more times, see if we can get it to respond. Well, that's a pity. But let's take a look where I was here. Let's connect to Helsinki again. So get load. So now it has already restarted and it's already ready. But if I do the get pods, and it says a few of these have been restarted. So what it means is it has detected that they have gone down, and now they are up again. But the cluster has recovered after the reboot and has reconnected itself, and it's running again. So it's not perfect. You still get some drops. It can definitely be improved with a better configuration on your balancer, but it kind of comes back to life. But I want to go now to 10 requests per second. So I can't do it with these servers. They are just too slow for my Pi calculations. So I'm going to try to do it live with you. Just get a new server, just get a complete blank server, install everything that is necessary, connect it to the cluster, and see if we can get to 10 requests per second. That's my goal. Let's see what happens there. So number one, I'm going to go to my cloud provider, this German company, which I can endorse. It's there, and I'm going to. They offer 3 locations. So I had one server in Helsinki, one in Nuremberg, and I'm going to get one in Falkenstein. And now the same size, which is 2 CPUs, 4 GB of RAM, and I'm going to connect it to the same internal network. And I think that should work. Oh, I should have changed the host name. No. Can I rename it? Yes. Yes, I like that. Okay. So I have my server here, and I also have like an internal load balancer where I'm going to connect the server to. So targets, servers, add server, this server, add target. So now it's also part of the balancer. So I have created the server, and now it should be getting my let's see, this is heads now. Should getting my password via email. Yes, so the server has been created. This is the IP. So SSH root at the IP and the password. Yes, I want to accept this. Connect. Okay, current password, new password. Okay, so now I have a Ubuntu server. Well, the host name is still wrong, but we'll deal with that. And I'm going to just do the stupid thing here, like Ubuntu Kubernetes 20.04, and just find the first link and just follow the instructions on how to install the packages, because that's what I've been doing, and not just to show you that it's not too hard. So we update, install Docker.io, copy, update. Come on. Yes. It should take less than 5 minutes, I hope. But let's see. Let's see how it goes. So installing Docker, I'm just going to copy paste commands like without looking too much. Start and enable Docker. And while this is running, I have this magic command. So the moment you create your first server with Kubernetes, you will receive a command like this one, kubeadm join blah 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 with a token and a certificate key. And this is basically the command that will allow you to get other servers into the same cluster. So I just keep a copy safe here in my email for everyone to see. and then I just need to copy paste this into the new server, and then I will make it join the cluster. But before we do that, we need to finish installing something. So start Docker, enable Docker. I think that's probably not necessary, but we'll do it. Where are we? So okay, more installs. More stuff here. And now another repository that we need to add. Okay. And now we install Kubernetes. Oh, what happened? Press the wrong key? Yes. No. And then it also says, oh, disable the swap memory because Kubernetes does not play well with swap memory, but it doesn't matter because our servers don't have swap by default. I think basically that finishes the setup of the server. When this is done, we should be able to try to connect to our cluster. There's one little detail that our password from when I created the cluster has probably expired. The certificate key has probably expired, so we just need to make a new one. But we do that with the second magic command, init phase upload. So we just need to go to the one of the other servers, like Helsinki, run this command. We get a new certificate that you can use to connect. Paste it in our new server. Copy this very long. String. No, probably a mistype. Okay, let's just use a text editor to fill this up. Certificate key, and then in the other server that is here, copy. So it's just a command to join our cluster, where you pass a URL and some tokens and a certificate key. And if I remember everything correctly, we should get a third member of our cluster. Okay, yeah, still take like basically we'll just copy all the configuration from the other servers into this one, so it becomes like a perfect copy. But first, it pulls some images and it does a few things. It takes I guess 2-3 minutes to finish all the job. And yeah, when we're done, we just need to tell, because we are now creating what's called like a master node. So we just need to tell this node, hey, you can also do work. You can also do worker nodes. And then we should be able to scale and run our app at 10 requests per second. That's my hope. We can get there. Yeah, now it's what it's doing. This might take a minute or two, depending on the speed of your internet connection. It's pulling images required for setting a Kubernetes cluster. You can also do it manually. Blah 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 blah. Well, let's hope this works. Meanwhile, I'm going to check that our seeds thing is still running. Yeah, it's back to life. Let's see how fast we are. 4.3, that's not very fast. Let's see if we'll repeat it a few times. Let's see if we get faster. Yeah, now it seems to be a bit faster. Yeah, we are now at 7. That's our reference with 2 servers. With 3, I think we should get a bit over 10. Yeah, so it's continued to do more bootstrap, more configuration part. Now a new etcd member. Oh, now it says that it's finished. So let's go to the other node where I have the kubectl command set up and get node. And it says that we now have 3 members of our cluster, and this one is not ready yet. So we have to wait a bit. Meanwhile, I'm going to take the replicas down, for example, to 2. And this is because I want to kill some. I want to make sure that Kubernetes serves all the efforts equally. Because when you get a new node, it will probably just don't pass any jobs to them until you make a new deployment. So that's a quick way of killing some of them. So now I'm going to do get pods. We are terminating some of these Docker containers, some of these Rails instances, and then we can scale back, and they should be split equally between the nodes. Let's see where we are. Get node. Oh, we are ready. Perfect. So now let's scale back to what? 12. Let's go with 9, 3 each. Let's see how it works. So we have a mix here of things going on. Some still terminate. Oh, now I think we have 9, right? Yeah, 9 seconds. They have started up and running. So let's try now. Let's see. We'll run a couple of runs. Let's see if we can get to improve our speed. So that was only 4 transactions per second. That was 7. Come on, run for me. Don't leave him here. Maybe it didn't put the jobs into the new node yet because it's still preparing something. We'll see. 7.7. Come on. I'm going to check here. Easy way. Stop. And while I run this. Yeah, it's not running Ruby here yet. It's not. It hasn't added any job to this. Oh, it's because I forgot one command. Yes. This is still acting as a master server because I told you I would change the setting, but I didn't. So taint. So you need to taint the nodes, like paint them, and say, hey, you are not master. Now you can also do job. And now this node will also do jobs. Okay. Let's scale back to like 2, and wait a bit. That's a little trick. And scale back to 9. Let's see. Yeah, now there's a huge mess, but in a few seconds, hopefully. Yeah, now it's Docker there, and there are some things running here. It's probably downloading the image from Docker Hub right now in our new server. Yeah, that's a lot of effort on Docker D. And soon we should have some Ruby instances running here.
So
Is there a kubectl command to see which nodes the pods are running on?
yes, but I can't remember that one. There is. But now we have three Ruby instances here.
Nice.
Good. So now let's run a few of these. They're still, I think, booting, so they're still loading stuff. Only 4 transactions per second. It's a bit better. 8:45. The last time. Come on, you can do this. Get to 10. Well, I'm happy with 9. The cluster did it. And basically, that's the end of my talk. Thank you very much. So, first of all, questions? Any questions about the topic? Has anybody have any experience with Kubernetes? Oh, Chris, go.
What about a managed cluster?
Like the ones that Google offers,
Yes.
where they do all the work for you. I haven't
Have you
used
tried
those.
those?
I have.
You don't get to be a managed cluster at all.
No, like
That's
this is
fine.
like no, the ones I think the ones we use at AWS are semi-managed. Like they take care of creating nodes and adding them to the cluster, but then they don't do anything else. Like it's basically they charge more for a job that takes like 5 minutes, like adding nodes. And they are supposed also to scale if the load goes. They just crash like normal. Like I haven't seen any big impact. There probably is, but I haven't seen a big improvement of those of that service that AWS provides. Any big difference of just renting your own servers. There probably is something, but it didn't help in our case. Any experiences with Kubernetes around here?
Only bad experience.
Only bad experience. You are on my team, yes. So I would not recommend it unless you have like a very good dedicated team configuring, checking, and looking at it every day. Even if it's the cool thing that someone will try to get into the project, wouldn't really recommend it. It's still fun to play with for some time. I have a yes, go.
Tiniest thing. If there are more than one, a multi-cluster, say many clients. There's a thing called Rancher,
Okay.
which is a multi-cluster Kubernetes playground.
Okay.
It's a web-based thingy that you like. These are pods, these are things, and so forth.
It's like Heroku, but a bit more managed solution. A bit of a
bit more like you run it on your own nodes.
Okay.
You decide which nodes you run it on. Okay.
Okay.
So Rancher is the thing.
I think it's more like a Docker dashboard that you could have before that they might have killed that, where you can just do deploys and say which container goes into which server and stuff like that. So it's, I used it.
Okay. So can you recommend it?
I can, yeah, not unrecommended. Yeah.
Okay. Okay. That's good. That's good. That's enough. Oh yes. So there is something called. I just got an email yesterday. Tech Day Barbecue. So there's like a conference and they are doing it digital, and we get free tickets for the Ruby Brigade. So if anyone is interested, you can check it out. Just